We will always have STEM with us, something will drop out of the public eye and go away. But there will always be science, engineering, and technology, and there will always be a mathematics. Welcome, everyone. Thank you for diving in the webinar today. My name is M. Asha, Assistant Professor, Department of English. It gives me immense pleasure to welcome our Secretary of SCPJC, Sri Lalit Kumar O. Jain, sir. Principal of SCPJC, Dr. V. Nagajodi sir, Vice Principal, Dr. N. Sujata ma'am, all the heads of the department, faculty members, and my dear students. Once again, welcome you all for this webinar. Today, Mathematics Department and IQAC are presenting a sneak peek into the future. Today's presentation will be about clean algebra by our expert resource person, Dr. M. Chandramouleeswaran, retired professor and head PG and research of Mathematics Department, Saiva Bonu Kesria College, Arupukotai. Luckily, the weather is on our side today. The sun and I are pleased to offer you a warm welcome. I would like to request Mrs. A. Elarisi ma'am to deliver the welcome address to the participants. Welcome, ma'am.
Good morning to all.
Good morning, Professor.
It's my pleasure to
Good
welcome
Good morning, Professor. Good morning.
today for the webinar on the topic clean algebra. I welcome the eminent speaker, Dr. M. Chandramouleeswaran, to share the knowledge with us. Welcome you, sir. I also welcome our Secretary, sir, Principal V. Nagajodi, sir, Vice Principal N. Sujata, ma'am, HODs and faculty members for this webinar. I would like to welcome all the participants who are excited to hear the ideas on the topic of the discussion. So let us have a great discussion ahead. Once again, I welcome you all. Thank you.
Thank you, ma'am. Leadership potential is in everyone. We all have it, but we all don't know it until we have a direct individual encounter with the Holy Spirit of God. The principal source of leadership influence is the Holy Spirit to us. It's my honor to welcome our principal of SCPJC, Dr. V. Nagajodi sir, to present the presidential address to the participants. Welcome, sir.
Thank you very much, Professor Asha ma'am. So, very good morning to all of you. On behalf of Sri Chandraprabhu Jain College, on behalf of our management, on behalf of myself, I cordially welcome Dr. M. Chandramouleeswaran, retired head of the department, PG and the research department of mathematics, Saiva Banu Kshatriya College, Arupukotai, for this national seminar on clean algebra. Mathematics is one science where all of us and all our walks of life, all technological advancements, all scientific principles are evolving around mathematics. So without mathematics, nothing is happening in this world, and particularly in this IT world, the most important aspect of our life revolves around mathematics. And today we have a very senior most expert in this field, and the sir is there with us. And it is a real privilege for us to have Professor M. Chandramouleeswaran, who is going to share his views on clean algebra. And our mathematics department is one of the very front runner in almost all aspects of our life. And I hope this particular session is going to provide a lot of insights into this mathematics. So with these few words, I express my sincere thanks to our chief guest and as well as to our management for granting permission to us, and as well as the head of the department, Dr. Kumar, and all his staff members and my dear students. I request all of you to please make use of this particular presentation through which sir is opening up our eyes, particularly on this new area which is known as clean algebra. So thank you very much, sir. Thank you very much to all of you.
Thank you, sir. A warm welcome to the head of the Department of Mathematics, Mr. S. Muthukumar sir, to introduce the resource person to the participants. Welcome, sir.
Thank you, ma'am. Good morning to all. I find immense pleasure in introducing our chief guest, Dr. M.Chandramouleeswaran, retired professor and head of the PG and Research Department of Mathematics, Sairabanu Sastriya College, Arupukotai. He completed his PhD in University of Madras and has got more than 32 years teaching experience and has guided 19 research scholars and 36 MPhil candidates. His area of specialization is associated algebra, semi-rings, and fuzzy algebra. He held many positions at the SPK College, Arupukotai. He served as the convener of UGC Planning Committee and a member in Curriculum Development Cell in MK University. He was a board member in the studies of various autonomous colleges like VVV College, Virudhunagar, SFR Colleges, Sivagasi, and also a chairman for PG Question Paper Setting Board, Vadhyasan University, Trichy. He was nominated as a subject expert by MK University for selecting staff to UGC. He had been the position of editor in International Journal of Mathematical Science and Application, International Journal Advances in Pure and Applied Mathematics, and also editor in chief for International Forum of Pure and Application Algebra. He published books containing the proceeding of national seminar and the current trends in mathematics in the year of 2014, and also one more book in 2015. He won 6 awards, to say a few. The best scientist award in recognition of the consistent of superior performance in mathematics by international multidisciplinary research in the year 2016 and 17, and also lifetime mathematician award by Forum D Mathematicians. So we have such a great mathematicians for today's webinar. Thank you, sir.
Thank you, sir, for your nice intro. Now, without further ado, I'll hand over the session to the chief guest to address the participants. Welcome, sir. Its session is yours.
Thank you. At the outset, I would like to extend my hearty thanks to Professor Nagajyoti and Professor Muthukumar for giving me a chance to share some of my ideas on mathematics. I would like to discuss with you KLENE algebra. As Professor Nagajyoti told, it's a current trend in IT also. So you will, at the end of this talk, you will see how this algebra plays a vital role in IT, that is namely cryptography. So we will just start with the brief introduction for KLENE algebra. KLENE algebra is an algebraic structure that axiomatizes the properties of a natural class of structures arising in logic and computer science. Actually, this algebra is named after Stephen KLENE, whose living years are 1909 to 1994, who among his many other achievements invented finite automata, that is finite state machines, regular expressions, the structures of fundamental importance in computer science. KLENE introduced this algebra in 1956, which was further developed by Conway in 1971. The algebraic system is used for calculating with sequential computation, choice, and finite iteration. Its classical application has been within the theory of formal languages, where it is one of many equivalent approaches in the description of regular languages. We will see what is meant by regular language and what is meant by formal language and semantic. Within the field of efficient algorithms, it has been applied to path problems on graphs, being closely related to the algebra of closed semirings, to convex hull algorithms and formal treatment of pointer algorithms. In compiler reconstruction, it can be used to prove the corrections of optimization technique for loop constructs. More recently, KLENE algebra has been successfully applied to the semantic description of imperative programs with a non-deterministic choice. Dropping one of the distributed requirements for KLENE algebra leads to a system that is close to process algebras. Finally, there are close connections to network algebra. Compared with the other algebraic approaches to semantics, such as relational algebra or sequential calculus, KLENE algebra and its relatives enjoy a particularly simple axiomatization, since they do not use a notion of pseudo-converse and the corresponding axioms. Since its basic features and rules are known even to a beginner of computer science, KLENE algebra will be more easily accepted than other formal systems and thus may serve as an effective vehicle for formal treatment of various subjects in computer science. Now, how this KLENE algebra arises? The KLENE algebra arises in the name of semirings. So many KLENE algebras appear in the guise of closed semirings, which are similar to the S algebras of Conway, also called KLENE semirings. Closed semirings and S algebras are defined in terms of an infinitary summation operator whose sole purpose, it seems, is to define the involution operator star. Thus, we recall some basic definitions from the theory of semirings. The notion of semirings was first introduced in the year 1934 by H.S. Vandiver while studying the algebra of ideals in rings. A semiring is an algebraic structure consisting of a non-empty set R on which we have defined two associative binary operations, addition and multiplication, such that the multiplication is distributive over addition. There are various ways of defining semiring, and the definition varies from person to person. Some may require that semiring should have zero element as well as identity, multiplicative identity. However, implicitly, semiring had appeared in studies on the theory of ideals of rings, on the approximation theory of natural numbers, and the non-negative rational numbers. So, why? How can we use this? This comes here. The most trivial example of a semiring, which is not a ring, is the first algebraic structure we encounter in life, namely the set of non-negative integers n, which also we call it as the natural numbers, with the usual addition and multiplication. Similarly, the set of non-negative real numbers with the usual addition and multiplication is a semiring, which is not a ring. The non-trivial examples of semirings first appear in work of German mathematician Richard Dedekind in 1894 in connection with the algebra of ideals of a commutative ring. For one can add and multiply two ideals, but one cannot subtract one ideal from the other, and were later studied independently by several algebraists, especially by the American mathematician H.S. Van der Waals. It is worth mentioning that N.H. Abel in 1826 itself considered some special kind of positive semifield over real numbers. In abstract algebra, a semiring is an algebraic structure similar to a ring, but without the requirement that each element must have an additive index. The term ring is also used occasionally, as this originated as a joke, suggesting that rings are rings without negative elements. So in life also we should remove the negativity from our mind. That is why I am preferring that concept of semirings to you. Semirings appear in natural manner and have been used to model many situations in which generalization of Boolean case was needed. More generally, the theory of semirings has been developed in five principal streams. The first stream is the pure theoretical investigations. In particular, linear algebra can be developed on semirings with important application in other branches of mathematics. Investigations related to theoretical arithmetic and number theory. Third area of specialization is investigations connected with logic in a broad sense, including non-algebraic structures. An algebraic approach to some theoretical and topological investigations and to the theory of differential equations, and that is namely idempotent analysis, control theory, etc. The other way of application is an algebraic tool for some investigation in the theories of cryptography, automata, formal language, theory of polynomials, optimization theory, graph theory, and other branches of applied mathematics. It is in this aspect that our talk today is going to address. Now we recall some basic definitions of semirings and discuss some examples. For if you need to understand the concept of KLENE algebra, you should pay. That is because a KLENE algebra, I can simply define it to be an idempotent semiring with additional construct, actually the involution. An example of this I can say as the set of all matrices under addition and over a positive integer. Over a positive integer, if you consider set of all matrices over the positive integers, then that matrices you can add and multiply. So it will form the semi-ring structure without any negative, additive negative inverse. Also, it has zero element as well as the multiplicative identity matrix. And apart from that, what is the involution on the collection of all 2 by 2 matrices? It is nothing but transpose of a given matrix or inverse of a given matrix. That is a unary operation that gives you the concept of semi-rings, and namely KLENE algebra structure. So I shall define formally the concept of semi-ring. Semi-ring, yes, addition and multiplication is an algebraic system with a non-empty set yes together with two binary operations, addition and multiplication, satisfying this condition. Yes under addition is a monoid, that is 0 is the additive identity. Yes under multiplication is a monoid with identity 1 and the distributive laws hold. And the fourth condition says that the additive identity is an absorbent or abortion, that it aborts everything. In many contexts, the semi-ring operation can be interpreted as follows: that addition stands for choice, multiplication stands for sequential composition, 0 stands for abortion, and so on. I think something we require more. Muthukumar, can I hide the videos? So the bottom two lines that may be missing for you. Okay, so these are some of the examples of semi-rings. I shall give more examples. The eighth one is the Boolean semi-ring, where the operations are given by the KLENE table. These Boolean operations correspond to the two logical operations and OR. The ninth example is an example from matrices. Let S be any semi-ring, then M2 of S is a set of all 2 by 2 matrices AB0A, where AB belongs to S. Then you can see that S is a semi-ring with usual addition and a multiplication of matrices. The last one is how we use this differential calculus of real valued functions. So let D of AB be the set of all infinitely differentiable real valued functions defined on AB. Under pointwise addition and multiplication of functions in D of AB, it becomes a semi-ring. Then we come to the concept of commutativity. See, we say that a semi-ring and S under addition and multiplication is additively commutative, is F under addition is a commutative semigroup, and if S under multiplication is a commutative semigroup, then S is said to be a multiplicatively commutative semigroup. The semi-ring S is said to be commutative if both S is additively commutative as well as multiplicatively commutative. These are some of the examples of additively commutative semi-ring, multiplicatively commutative semi-rings, and commutative semi-rings. Then the last one is additively left cancellative. So this is a weaker condition for finding the inverse of an element in semi-ring. Okay, so it chooses a semi-ring S under addition and multiplication. Choose an element alpha of S. Then we say that alpha is said to be additively left cancellative if it satisfies the following rule: alpha plus beta equal to alpha plus gamma implies beta should be equal to gamma. Then it is said to be additively right cancellative if for all three elements alpha, beta, and gamma in semi-ring S. We say that we have beta plus alpha equal to gamma plus alpha implies beta equal to gamma. If every element alpha of a semi-ring S is additively left cancellative, then the semi-ring is said to be additively left cancellative semi-ring. If every element of a semi-ring S is additively right cancellative, then the semi-ring is called an additively right cancellative semi-ring. The semi-ring S is additively cancellative if it is both additively left as well as additively right cancellative semi-rings. Analogously, we can define the multiplicatively cancellative semi-ring as follows. Okay, and with the definition of additively cancellative semi-ring as well as multiplicatively cancellative semi-ring, we can say that a semi-ring S is said to be cancellative if it is both additively and multiplicatively cancellative. Then comes the definition of a sub-semi-ring. So consider the semi-ring as any subset, non-empty subset A of S is said to be a sub-semi-ring if it contains both the additive identity and the multiplicative identity and is also closed under the two operations of addition and multiplication. This is an example of a subsymmetry. Next comes the definition of a left ideal. Number one, the first condition is the multiplicity identity should not be an element in it. This you can see in any algebra text. If that identity, multiplicity identity belong to the ideal, then the ideal becomes the whole of the ring. That is naturally the concept that you believe in. So, in order to define the left ideal of symmetry, identity, multiplicity identity should not be an element in the subset. Then it should be closed under addition. The third condition is if you choose one element from the subset and another element from semi-ring, yes, then the product SA should be an element in the subset. The element of S acts from the left, that's why we call it as a left ideal, and this example of a left ideal from the set of matrices. Then, on the other hand, if you replace the third condition, A in I and S in S implies AS belong to I, then you call such a subset I to be a right ideal, as seen in the definition of 11. And this is an example of a right ideal of the semi-ring of 2 by 2 matrices over the positive integers. A non-empty subset I of the semi-ring S is said to be an ideal if it is both a left and a right ideal of S. Then usually you call this prime semi-ring, semi-prime semi-ring, and two torsion free semi-ring. This two torsion free semi-ring is a new concept that one should cross. A semi-ring S is said to be a two torsion free semi-ring if 2 into A equal to 0, where A belongs to S, implies A equal to 0. That means if whenever you add that element twice, then it should be, if the summation is 0, then every element should also be equal to 0. This is a two torsion free semi-ring. Then we consider the concept of left singular semi-ring. A semi-ring S is said to be a left singular semi-ring if the two semigroups S under addition and S under multiplication are left singular. That means S under addition is left singular, means A plus B equal to A for all AB in S, and left under S under multiplication is left singular if we have A into B equal to A for all AB in S. Similarly, you can define right singular semi-rings if the two groups are right and two semigroups are right singular. Then we say that if both the semigroups S under addition and S under multiplication are left as well as right singular, then the semi-ring itself is said to be a singular semi-ring. Now comes to that important role with which we define the concept of KLENE algebra. See, idempotent semi-rings appeared firstly in the theory of finite automata in the year 1956. That is a paper by KLENE. Nowadays, they provide a natural framework for analyzing a broad class of discrete even dynamical systems such as the design and analysis of bus and railway timetables, scheduling of high throughput industrial operations, solution of combinatorial optimization problem, the analysis and improvement of flow systems in communication networks. There are not many known applications of multiplicatively idempotent semi-rings here. However, we have some applications in the case of additively idempotent semi-rings. Now, for instance, particular multiple idempotent semi-rings play an important role in some applications in three-valued logic, where the connective conjunction is considered as infimum, but disjunction is not assumed. What do you mean by three-valued logic? Normally, we will be using the Boolean logic, true or false. The three-valued logic includes one concept that is possible. So, in the three-valued logic, we have three operations, three results. One is true, possible, and other one is false. These are the three conditions, three values of the three-valued logics. Such logics are applied in problems connected with preference talks. So naturally, if I ask some of you to answer one question, either you can answer correctly or you can answer wrongly. The third possibility is you may be partially correct or partial. That you can try. That is possibility. You can try an answer, but not a correct or a correct answer, not a false answer. And additively idempotent semi-rings are used in cryptography as a platform for cryptographic schemes. How to define an additively idempotent semi-ring? A semi-ring S is said to be additively idempotent if A plus A equal to A for all A in S. If A into A equal to A for every element of A in S, then we call the semi-ring S is to be multiplicatively idempotent semi-ring. In general, the semi-ring S is said to be an idempotent semi-ring if it is both additively as well as multiplicatively idempotent. One thing that you should have, every semi-ring need not be a partially ordered semi-ring. That is, there is no partial order relation in a semi-ring. However, every semi-ring has a canonical preorder defined as follows. Consider the semi-ring S. Take two elements A, B in S. A is said to be canonically preordered to B, denoted by A pre-check B, if there exists an element C in S such that A plus B equal to C. An idempotent semi-ring has a partial order relation defined by A less than or equal to B if A plus B equal to B. Up to isomorphism, there is a printing mistake here, A plus B equal to B. Up to isomorphism, there are 6 additively idempotent semi-rings of order 2 and 6 multiplicative idempotent semi-rings of order 2. As is well known, additive and multiplicative idempotents are independent conditions, and there are many examples of semi-rings which satisfy one of these conditions but not the other. I shall give some examples here. The first example of the semi-ring, see here the semi-ring S contains only the two elements 0 and 1. That is, we are considering only the Boolean semi-rings. So at this semi-ring under this KLE table is an additively idempotent semi-ring but not a multiplicatively idempotent semi-ring. The next example is an example for a multiplicatively idempotent semi-ring but not an additively idempotent semi-ring. The third example is a semi-ring which is both additively as well as multiplicatively idempotent semi-ring. The fourth one is a semi-ring which is neither additively idempotent nor multiplicatively idempotent semi-ring. Now we come to the main section, KLENE algebra. We will discuss some definitions and examples. There is some disagreement regarding the definition of KLENE algebra. The literature contains several inequivalent definitions. However, we have the following definition of KLENE algebra. A KLENE algebra is an idempotent semi-ring K with the usual addition and multiplication operation as well as the unary operations involution, that is 0 and 1 with identities, such that there exists a unary operation star that satisfies the following conditions. A plus B, that involute of A plus B equal to A involute of A plus involute of B, and involute of A into B equal to involute of B into involute of A. This resembles that transpose operation as I told in the example of 2 by 2 matrices. And the third one is involute of an element is same, and these other inequalities are satisfied. This is the definition for KLENE algebra. A KLENE algebra is called star continuous, that is involute continuous, if it satisfies the axiom x y involute z equal to supremum of x y power n into z, where n greater than or equal to 0 for any x y z in K, where y power 0 equal to 1. And how do we define that power y power n plus 1? Y power n plus 1 is defined as the product y into y power n, and the supremum is with respect to the natural order. Now, this is the example of a semi-ring. So, we will just consider the collection of all finite length strings over a finite alphabet, including the null string, which is denoted by epsilon. The set sigma star forms a KLENE algebra under the following operations. So, this is the example for KLENE algebra. Thus, the operation multiplication is applied to two sets of strings A and B, that is, products or the sets of all strings obtained by concatenating a string from A with a string from B in that order. Thus, A star is the union of all powers of A, equal to A star consists of all strings obtained by concatenating together any finite collection of strings from A in any order. Any subset of the full power set of sigma star containing the empty set and the null set, that is, this set singleton empty, so that contains only singleton space character or blank space, and closed under the operations is a Kleene algebra. This is another example of a Kleene algebra, which we can use that min plus operation. Min stands for the additive operation of the semi-ring, and a multiplication is denoted by the addition in the reals. This is another operation. And the star is that 1 equal to g. Kleene algebras abound in computer science. An important example of a Kleene algebra is the collection of the family of regular sets over a finite alphabet, which I have defined earlier. The equational theory of this structure has been called the algebra of regular events. This theory was first studied by Kleene, who posed the axiomatization as an open problem. Then, the second example is the area of relational algebra, the family of binary relations on a set with the operations of union, addition, union for addition, relational composition, uh, or star yes for the multiplication, and the empty relation for 0, the identity relation for 1, and the reflective transitive closure for the involutory operation, that is unary operation, star, which constitute a Kleene algebra. The third example is in semantics and logics of programs, where we use Kleene's algebra to model programs in dynamic logic and dynamic algebras. In the design and analysis of algorithms, namely, you consider n by n Boolean matrices, and the matrices over the so-called min plus algebra are used to derive efficient algorithm for reachability and shortest paths in directed graphs. The fifth case is a Kleene algebra in which addition gives the vector sum of two polygons and the multiplication gives the convex hull of the union of two polygons, has been used to solve a cycle problem in graphs. And these are dealt in references 12 also. Then I shall deal some of the things in semantics. First one is semantics. What do you mean by semantic? Semantic means the meaning and interpretation of words, signs, sentence structure. Semantics largely determine our reading comprehension, how we understand others, and even what decisions we make as a result of our interpretations. Semantics can also refer to the branch of study within linguistics that deals with the language and how we understand it. This has been a particularly interesting field for philosophers as they debate the essence of meaning, how we build meaning, how we share meaning with others, and how meaning changes over time. The proportions and actions are connected by modal operators that map actions and proportions of proportions. To prepare this model view, let's consider a semi-ring element that describe an action or abstract program, and P describe a proportion or assertion, also called a test. Then P A describes a restricted program that acts like P into A. That should be taken as P into A. P into A describes a restricted program that acts like A when the initial state satisfies P and aborts otherwise. Systematically, AP describes a restriction of A in its possible final states. An abstract domain operator is an assignment to A, the test that described precisely its enabling status. In combination with the restriction, the domain operation yields an abstract pre-image operations. This provides the semantic basis for modalities. Then comes the concept of relational algebra, which is another example for Kleene algebra. A relational identity is a pair of two relational expressions whose interpretations give two identical operators is said to be complete if and only if one can define from it every possible relational identity using only deductions involving uh, use, usual relational manipulations and relation substitutions. Then relational algebra, what do you mean by this? Relational algebra is a procedural query language like DBase or database, or sometimes the Python or C++ which we can take. So, procedural query language, it takes instances of relations as input and yields instances of relations as output. It uses operators to perform queries. An operator can be either unary or binary. They accept relations as their input and yield relations as their output. Relational algebra is performed recursively on a relation, and intermediate results are also considered relations. This is that loop considered that we consider in that. The fundamental operations of relational algebra are as follows: select operation, project operation, union operation. The select operation selects tuples that satisfy the given predicate from a relation. It is denoted by sigma p of R, where sigma stands for selection predicate and R stands for relation. P is the proportional logic formula which we may use to connectors like and, or, and not. These terms may use relational operators like equal to, not equal to, greater than or equal to, greater than, less than, or less than or equal to. Then the project operator, it projects columns that satisfy a given predicate. See, you can apply this in MS Excel if you are well versed in that one. It is denoted by this one, where you can select one particular row or column that satisfies a given criteria. So that is denoted by pi A1, A2, AR, AN of R, where A1, A2, etc. AN are attribute names of the relation R. Then comes the union operation. It performs binary union between two given relations R and S, which is defined as R union S equal to the relation T, where T either belongs to R or T belongs to S. Then for union operation to be valid, not in general it is valid, as you see in group theory also, union of two subgroups may not be a subgroup. So here too, the union operation is to be valid, the following conditions must hold. R and S must have the same number of attributes. Then the attribute domains must be compatible. The third condition is duplicate tuples are automatically eliminated, as it is the something like set concept. Then the fourth operation in the relational algebra is the set difference operator, and the fifth one is the Cartesian operator that you can have. The sixth one is rename operation. The results of relational algebra are also relations, but without any name. The rename operation allows us to rename the output relation. Rename operation is denoted by row. That is row A of E, where the result expression E is saved with the name. Additional operations on relational algebra are set intersection, assignment, and natural join. Then comes the concept of regular set. You choose an alphabet set by A, which is a finite non-empty set of symbols. These symbols may also be called as tokens. Empty set is not an alphabet. A finite sequence of symbols from some alphabet set A is called a string. The number of symbols appearing in a string W is called the length of the string and is denoted by this notation. For any alphabetic set A, all strings of length k, where k greater than or equal to 1, is denoted by A power k or A star. That is A power k. I shall fix this notation, not A star. This is A power k. That is A power k is a collection of all strings W, where the W is a string of length k. Now consider two strings W1 and W2. Then the concatenation of W2 with W1 is a string denoted by W1 W2, which is the string W1 followed by W2, and the length of the string the W1 W2 is the sum of the lengths of the two symbols. two strings. For example, you just consider W1 to be the string ABC and W2 to be the string XYZ from the alphabetic set of English. Then we write W1, W2 equal to ABC, XYZ. A string obtained by removing one or more trailing symbols is called a prefix. That is, if I choose this W1, I can remove A, I can remove AB, I can remove ABC itself, full thing. Similarly, suffix of a string is defined as a string obtained by removing zero or more leading symbols. The leading symbols are here are C. So I can remove C, or I can remove BC, or I can remove totally ABC. That is the one. So any string obtained by removing a prefix and a suffix from a given string W is called the substring of W. A language L over the alphabet set A is a collection of all strings over the alphabet A. That set empty and the singleton blank space are languages where M null set is undefined, and this set is a language without any string. Let L be a language or alphabet set, then clean closure of L, which we denote it by L star, is defined as follows. L star is defined as the smallest algebra that contains the given Kleene algebra. That is the concept that you have to consider. Right. So this is the concept of regular expressions, which I already mentioned. This gives the concept of finite automata. The language accepted by FA here means finite automata or finite state machines. So the language accepted by finite automata are regular languages which can easily be described by simple expressions called regular expressions. We have some algebraic notations to represent the regular expressions. Regular expressions are means to represent certain sets of strings in some algebraic manner and describe the language accepted by FA. For example, if A is an alphabet set, then the regular expressions over this can be described by following rules. Any symbol from A or empty or null are regular expressions. If R1 and R2 are two regular expressions, then union of these two relations are represented as R1 union R2 or R1 plus R2 is a regular expression. If R1 and R2 are two regular expressions, then their concatenation is also a regular expression. The Kleene closure of a regular expression denoted by R star is also a regular expression. If R is a regular expression, then the set generated by this regular expression is also a regular expression. The regular expressions obtained by applying rules 1 to 5 once or more than once are also regular expressions. With the help of these regular strings, we can define the formal language. The formal language is a collection of strings of symbols drawn from a finite alphabet. There are two ways to specify a formal language. One way is by setting a fixed rule that generates a language. The second one is for a formal machine that recognizes the language normally. Formal language will have precise syntax and semantics which are used to instruct simply. Formal language simply or instruct. Simply, a formal language is a programming language. Then the final one, I shall end up with this real life application of Kleene algebra. Why should we study Kleene algebra? One particular example of a Kleene algebra is the min plus algebra, also called a tropical symmetry. Min plus algebra finds its application in various fields such as transportation, manufacturing, and information technology. In the case of transportation, the algebra is used to minimize the transportation cost. In the case of information technology, it is applied to build a protocol for keeping secret information. This method adopts an algorithm from Stickel's key exchange protocol. Sorry, just bear with me. The rapid development in information technology forces us to ensure that our information is more secure to keep secrecy of the information. Many ways are developed to developed by several experts under the common name cryptography. There are two systems in cryptography, namely symmetric and asymmetric cryptography. The symmetric cryptography uses the same key, private key or secret key, to encrypt and decrypt the information. It allows that a key or password, the most important notion of the system. Every party that wants to exchange a secret message must agree on the same key. Considering the importance of the key, different methods based on groups, semi-rings, matrices, and other mathematical systems have been developed. One of the important and well-known methods of symmetric cryptography to establish how to share secret key was the Diffie-Hellman method developed by Whitfield Diffie and Martin Hellman in the year 1976. This method allows two parties to establish a secret key over an insecure communication channel. The concept of a key agreement protocol that uses the theory of non-commutativity is the one used by Grigory D. and Vladimir S. in the year 2012. Strickle proposed a key agreement protocol based on non-commutativity. This paper describes an analogous of Strickle's key exchange protocol that uses the semi-ring of matrices over a semi-ring that incorporate new binary operations, namely tropical addition and tropical min plus operation, or called a tropical semi-ring. The first step in a crypto system is to label all possible plain text message units and all possible ciphertext message units by means of mathematical objects from which the ciphering transformation and deciphering transformation can easily be constructed. There are several techniques available in the literature to construct these structures. In practice, one can have an equipment for enciphering and deciphering which is constructed to implement only one type of crypto system. Over a period of time, the information about the types of systems they are using be leaked out. To increase the security, they need to change frequently the choice of parameters used with the system. The parameter is called a key or secret key. If in the system the two parties agree on a common key prior to transmitting the information, such a scheme is called a symmetric cipher system. In the symmetric encryption, the plain text is encrypted by using the key, and the same key is used to decrypt the message. This technique is easier to use but less secure. Moreover, a safe method of transferring the key from one party to another has to be identified. This scheme is described by the following diagram. On the other hand, in the asymmetric cipher system, the plain text will be encrypted by using two keys, namely public key and the private key. This technique uses two different keys to encrypt and decrypt the plain text. The process of this scheme is slower, but it provides confidentiality and authenticity. Examples of asymmetric key encryptions are Diffie-Hellman, Algebra, and RSA techniques. This scheme is described in the following diagram. Data that can be read and understood without any special message. I shall have described a plain text and a teacher. Now comes this. Cryptography is the science of using mathematics to encrypt and decrypt the data. Here I shall give one particular one. This we call it as a group action problem. Namely, you consider a cyclic group in particular. So the discrete logarithms are simply logarithms in cryptography that are defined with regard to multiplicative cyclic groups. Given a finite group G and the elements G and H in G, we have to find a first integer, a natural number n in n, such that G power n equal to H. The above problem has a solution if and only if H belongs to the cyclic subgroup generated by G. If H belongs to the cyclic subgroup generated by A, then there is a unique integer n satisfying the condition such that G power n equal to H. We call this unique integer the discrete logarithm of H with base G. Before the discovery of the public key system, the two parties wishing to communicate will meet beforehand to agree upon a secret key. This severely limits the spontaneity of secured communication and may require a courier. The origin of using the DLP in cryptographic scheme is due to Diffie-Hellman. I have told all this earlier. So here, so let m be a large integer, say which is greater than 10 power 14. So how to construct the key construction between two parties A and B using the Diffie-Hellman procedure? This is given by the next slide. A chooses a random integer x with x lying between 0 and m, computes g power x and sends the result to B which, while keeping x as secret. B chooses a random integer y with this condition. He computes g power y and sends the result A keeping y secret. This g power x and g power y are called public keys while x and y are called private keys. Both A and B construct the key from g power xy, which A computes from g power y raised to the power x and B computes from g power x raised to the power y. If this scheme is to be secure, then the problem of computing g power xy from the knowledge of g power x and g power y should be intractable. We shall refer this problem as the Diffie-Hellman problem. It is clear that solving the underlying discrete logarithmic problem is sufficient for breaking the Diffie-Hellman protocol. For this reason, researchers have been searching for groups where the discrete logarithmic problem is considered a computationally difficult problem. In the literature, many groups have been proposed as candidates for studying the discrete logarithm problem. The discrete logarithm problem over a group can be seen as a special instance of an action by a semigroup. The interesting thing is that every semigroup action by an abelian group rises to a Diffie-Hellman key exchange. Okay, so the primary objective of an adversary who wishes to attack a public key encryption scheme is to systematically recover the plain text from ciphertext intended for some other entity. If this is achieved, the encryption scheme is informally said to have been broken. A more ambitious objective is key recovery, to recover A's private key. If this is achieved, the encryption key scheme is informally said to have been completely broken. So this is the definition for group action, and this is the definition for stabilizer and also the orbit of this one. The next comes the definition of a discrete logarithmic problem, which I already told, and this one is a semigroup action problem. You choose a given semigroup G, act it on S, and the element x in S, y in Gx, the orbit, find G in G such that Gx equal to y. This problem is the analogous of discrete logarithmic program at semigroup action problem. If I replace this semigroup by a semiring, the problem becomes a semiring action problem. So this is another definition where I have defined the concept of min plus algebra on matrices over any semiring. So consider the semiring S under addition and multiplication. Using this addition and multiplication of S, I will define a new semiring MP of S, the set of all P by P matrices with entries from S. We define tropical addition and multiplication as follows. Then it becomes a tropical algebra where the involution operation is, as I already told, the transpose or inverse operator. Then we will now present a protocol for this tropical semiring. Now this you consider, and these are the things that I already mentioned. Okay, I'm sorry, repeated things. Then in tropical algebra, the addition, that is tropical addition, is not invertible. That is min is not invertible. Min operation is not invertible. Now I share a protocol that uses the tropical semiring of P by P matrices, which is a simpler example of a KLENE algebra. I shall consider a semiring S under addition and multiplication, construct the tropical semiring of P by P matrices, then define a mapping phi from S to B of Ni, where N is the cardinality of A. What is this B of Ni? B of Ni is a semiring that uses N alphabets and if n is the number of alphabets in that one, I lies between 0 and n, okay, and this one will be I modulo. You have to choose. See, you take two elements a and b in b of ni. The sum a plus b is taken to be equal to a plus b if a plus b is less than n, and if it is greater than n, you have to choose modulo I. You have to choose modulo. So it will be equal to C, where C equal to A plus B modulo I. Similarly, you can define the multiplication operation in such a way this B of Ni is a symmetric, which I have explicitly omitted in this paper. So you define a mapping. So here, for our example, I shall show in later on. So you define a mapping. This is a one-way function. Then you choose two elements in the tropical matrix that they are public matrices, or sometimes you call it as a public. Alice chooses two tropical polynomials P1 of x and P2 of x over S and find the values P1 of A and P2 of B. Then she calculates P1 of A tropical multiplication, tropical addition P2 of B, tropical multiplication P2 of B, and send it to Bob. Bob chooses two tropical polynomials Q1 of x and Q2 of x over S and finds the values Q1 of A and Q2 of B. Then he calculates Q1 of A tropical addition Q2 of B and send it to Alex. Alex calculates this one, Bob calculates this one. Both of them get a common n by n matrix, p by p matrix, which is represented by this one. The common key is then the image of the above matrix under the mapping 5 from S to B of Ni. Then we obtain the common key as follows. The common key obtained above is used to encrypt the plain text to a ciphertext and decrypt the ciphertext to obtain a plain text. This is the encoding method. Consider a plain text P. AP with a set of alphabets in the plain text. We define this mapping, then obtain the encoder matrix, then use the key to define the ciphertext, then Alice sends the cipher matrix C to this. Bob decrypts using the matrix Cij plus Kij. By this way, Bob decrypts all entries in the cipher matrix and decoded it by using the inverse function psi inverse from range of psi to AP. By this way, he obtains the plain text. For example, you consider the semi-ring A. Okay, this is the semi-ring that you obtain. So you can observe that this is an additively idempotent semi-ring. A plus A equal to A, B plus B equal to B, C plus C equal to C, D plus D equal to D, E plus E equal to E. This is an additively idempotent semi-ring, while this is not a multiplicatively idempotent semi-ring. Okay, and this is the canonical preorder. That means it satisfies 0 is less than or equal to everyone. That means you can add every element to obtain them. So A is less than or equal to A. That means A can add A to obtain this. This is the canonical preorder. Then you consider the 2 by 2 tropical matrices, tropical semi-ring of 2 by 2 matrices over the elements from S. So consider that elements. I'm sorry, I shall come back to this one. So you choose the element 2 by 2 matrices. The set semi-ring consists of the 6 characters 0, A, B, C, D, and E. Then comes this one. Now we define 5 from S to B of 27, 7. I have chosen I as 7 and 27, that means English alphabet, namely 26, and one's alphabet for blank space. So 5 of 0, that is the empty space, which is mapped to 0, 0. 5 of A to be mapped to 14 in B of 27, 7. 5 of B equal to 22. 5 of C equal to this one. Then you choose that matrix A equal to BDEC and B equal to DAEB as public matrices or public key. Alice chooses two tropical polynomials over S as P1 of x equal to X tropical matrix X plus tropical addition B cross X plus E and P2 of X like this. Now Alice finds P1 of A and P2 of B and calculates the tropical addition P1 of A, tropical multiplication P1 of A, P2 of B. Bob similarly chooses two tropical polynomials Q1 of x and Q2 of x. He finds Q1 of A, Q2 of B and finds the product. Then Bob sends this to Alice. Alice calculates this one. Bob calculates this one. If you observe that last two calculations are the same, then the common key is obtained. After using this common key, we will be using to change. For example, let us consider the plain text as hello. So Alice needs to send a message hello to Bob. Let it be the plain text. Then what are the alphabets contained in this HELLO, HELO? Then she defines that mapping psi from AB by psi of h equal to 0A. That is the order of that alphabet in that one. By using psi, we get the 2 by 2 encoded matrix like this. Each entry Bij of this encoded matrix can be encrypted as Bij plus order of Kij minus 1 into Kij. Kij is the common key and get the cipher matrix C. Alice sends this ciphertext to Bob. Bob decrypts the entry of C by Cij plus Kij and gets the encoded matrix. Then plain text is obtained by inversing this one. So this is the way he obtains the original plain text. These are the references for this particular topic. Thank you for your patience. Thank you, Mananda. Any questions?
Thank you so much, sir. It was a wonderful session for us. So, students asked a question to you.
Uh,
Can you suggest any particular research area in clean algebra?
Actually, I have suggested one particular area where we are working, that is cryptography.
And another
One,
questions are there. Thank
yeah,
you so much, sir. Suggest a research area of application of clean algebra in formal language.
yeah, yeah, formal languages. You have to find idempotent seminar. So you have to find idempotent siblings. I have already mentioned in my talk that there are six idempotent elements, isomorphic idempotent elements, additively idempotent, as well as six additively idempotent clean algebra or semi-rings up to isomorphism with the two symbols 0 and 1. Then if you go for the next level, that is if you use three symbols, it will be a difficult problem, it will be a very difficult problem. You can choose three elements and find additively idempotent semirings using these three elements, and you can find the number of isomorphic idempotent semirings using the three symbols. Okay, that itself is a good research problem. Also, you can apply this in transportation problem or assignment scheduling problem, or even at your college level, that timetabling problem. They are used the formal languages, and it's a really graphical oriented problem. So you can also connect graph theory with your plain algebra also.
Thank you, sir.
Thank you.
Now it's time to word of gratitude. Gratitude means to recognize the good in your life. Be thankful for whatever you have. Some people may not even have one of those things you consider precious to you, love, family, friends, and etc. Each day, give thanks for the gift of life. You are blessed then. Now, I would request Dr. S. Vijay Chitra, Assistant Professor, Department of Mathematics, to propose the word of gratitude. Welcome,
Sorry for
ma'am.
interruption. Before you propose vote of thanks to me, let me propose my vote of thanks to Professor Nagajodi and also Professor Muthukumar for giving me this opportunity. I
Thank you
think,
so much, sir. Shall we proceed?
yeah.
Thank you so much. Welcome, ma'am.
Good afternoon, everyone. I feel mathematics is the only place where truth and beauty mean the same thing. On behalf of Department of Mathematics and IQAC, I extend a really Hearty vote of thanks to our chief guest who spared time to grace this occasion. Thank you very much, sir, for your informative session. You really give deep insight into the topic and reveal certain interesting facts. Thank you, sir. My gratitude to our secretary Lalit Kumar Ojain for his words of encouragement. I thank our principal Dr. V. Nagajodi and vice principal Dr. N. Sujata for their unstinted support for this program. My heartfelt thanks to the heads of various departments and the faculty for their valuable contribution in all our efforts. I thank our system engineer P. Balaji and his team for their technical support. My special thanks to M. Asha Devi, Assistant Professor, Department of English, for her constant support. Last but not the least, I thank all the participants for your cooperation in making this webinar a resounding success. Once again, I thank you all for your attention. Thank you.
Thank you so
Shall I?
much, ma'am.
Okay, let me leave.
Yes, sir. Yes, you can leave. Principal, sir.
You can stop the live. Ask them to stop the live.